So here we have the aircraft in its weight and balance configuration, and right now the CG is about 25% of the mean aerodynamic chord, and we can change it. We can bring it forward and make it a rather nose-heavy configuration, as you can see now, or we can take it back up to about positive 0.15 and have it just before it tips over. So the aircraft mass can be calculated by hand as such, and likewise with the center of mass. What was found was the center of mass is about 2.5 centimeters off in this method, so it has to be counted for as an inaccuracy in the simulation perhaps. So this next section is a static thrust test of the aircraft, and as you'll shortly see, the thrust will peak at about 20 newtons maximum. However, the throttle and thrust are not linear, and this will have to be accounted for by the pilots. And the following graphs, they show the relationship being exponential between thrust and throttle. Now, controlled surface deflection check will be performed, and as you can see, different deflections will be plotted in this window here. So this is pitch up, pitch down, and then roll left, roll right, yaw right, and finally yaw left. This section here conducts a longitudinal dynamic response test of the aircraft, and as you can see, the aircraft control surfaces are manipulated and it responds accordingly. The short period frequency can be determined from this graph here, and it's determined to be about 7.9, a bit lower than the theoretical prediction. And likewise, the damping ratio is predicted to be about 0.76, once again a bit lower than the theoretical prediction. Making the aircraft fly faster will make it longitudinally more responsive, as can be seen. So the pilot has to be more sensitive with the controls, whereas making it slower, closer to the stall speed, makes it very hard to have pitch up control. A little bit easier with the pitch down, but the response is much slower. Varying the location of the CG will affect how controllable the aircraft is, and as can be seen, putting the CG rather forward of the aircraft makes it very stable. Perhaps this level of stability might make it difficult to control the aircraft in pitch, whereas slowly moving it backwards makes the aircraft a little less stable, but also much more controllable, as can be seen. However, there is a limit, perhaps at around 32% of mean aerodynamic chord, the CG being placed there. The aircraft is just barely stable enough to control, and putting the CG any further back will, as will be demonstrated, make the aircraft very unstable and controllable, whereas pitch control makes the aircraft forcefully roll, and it makes it rather unstable for the pilot to fly. The lateral dynamic response of the aircraft shows that the deflection of rudder pedals are providing the correct side slip angles. Likewise, the deflection of the ailerons are providing the correct roll directions, as demonstrated here. And varying the flight speed would also change the response of the aircraft's lateral motion, so slowing it down obviously makes the controls much less responsive, whereas speeding up the flight speed would make the lateral controls much more responsive. This section will help determine a vertical center of mass position to achieve zero thrust pitch coupling. So as can be seen, having the center of mass relatively high up at about minus 0.09 meters makes the aircraft respond quite heavily with the pitch as thrust is varied. However, as we start to reduce the vertical position of the center of mass, we notice that the pitching response is reduced, and once we achieve a value of about minus 0.03 to minus 0.02, the pitching response of the aircraft is almost zero, and thus placing the center of mass in this region will provide the pilot with added stability and no issues from varying the thrust in flight, so the trim would be maintained for much longer without needing to retrim after every thrust change. The lift curve shows that an angle of attack of 10 degrees must not be exceeded to avoid stall. And the drag polar shows that a drag of 0.1 would provide highest lift, whereas pitching moment is telling us that having an elevator deflection of 5 degrees would provide the most stable control of the aircraft, and the pitching stability shows that the COM position must be less than 0.6 to avoid stability issues. And this plot over here just shows that L over D is maximized at a CL of just less than 0.5. The aircraft, while taxiing, faces no steering danger, as there is no steering control on the aircraft while taxiing, and as such, the aircraft cannot be controlled while on the ground. Without flaps, the aircraft will take off at about a speed of 18 meters per second. It struggles a little bit at first, but it does unstick from the ground. Whereas with flaps deployed, as will be shown, the aircraft takes off at a speed of about 15 meters per second, which is quite a bit slower than the unflapped speed, and will definitely assist the aircraft in takeoff and short field performance. A throttle of about 55% allows the aircraft to fly trimmed in cruise, as is demonstrated here. The aircraft's phugoid frequency is about 0.1 Hz, and as is shown in this demonstration, the aircraft naturally restores itself in this phugoidal state without requiring corrections from the pilot. The aircraft has a minimum trim speed of about 17 meters per second, as configured here, whereas a maximum trim speed of about 45 meters per second can be achieved in this configuration. The aircraft is now being taken for a short flight around the field. As can be seen, the takeoff performance is really good. However, it is a little bit difficult to control at first, and I myself, being not the best trained pilot, am struggling a little bit with the trim. Once the flaps go in, the aircraft is sort of reconfigured once again, retrimmed, and it's a bit of a struggle. However, as can be seen, the aircraft is very responsive. It's not helpful that there is no variable aileron control, as in the keyboard controls simply input 100% of the control surfaces. As the aircraft comes in to land, you can see on the screen that there's a lot of control inputs being made. It's a stable aircraft, but it still needs a lot of control to maintain its attitude. And once the flaps are deployed, once again there's been a retrim, and it is a bit of a struggle to get the aircraft back into a new trim. And I'm making my best effort to land as close as possible to the hangar. The view is a bit blocked as the camera is being blocked by the hangar walls, and the landing isn't the smoothest, as can be seen. But in the hands of a skilled pilot, this plane would fly really well.